What is a reaction quotient, and how is it similar and different than an equilibrium constant that I've talked about in my other previous videos for equilibrium? So in Unit 7 called Equilibrium, in Section 3, we are going to cover this topic in AP Chemistry, or this might be in your college level chemistry class. And in this one-page set of notes, we're going to cover what is the reaction quotient using the definition and a graph. How can we compare that to a data table where we can find what's called the reaction quotient and the equilibrium constant? And then how can we do the same thing but a little different using some particle views? All right, so in this little set of one page of notes, that's the three things that we're going to be talking about in this video. All right, so first let's just do the basics. What is a reaction quotient? So it's the letter Q. So that's the letter that we use, reaction quotient. And then how do you calculate it? Well, this is what's kind of easy and interesting, is that we calculate it the same way we calculate the equilibrium constant, K. So it's the product. So for the reaction I have above, AB is my product as a gas, and we could have a pressure or a concentration. Let's just say we have the concentrations. And then the reactants are in the denominator, but we only have A because in a previous video I talked about how we don't put solids or liquids, pure solids or liquids, in the K value, nor do we put them in the Q value. I'm just going to zoom in a little bit. What if we wanted to say this was a QP? Then what we would do is we just do the same thing. We just have to say it's the partial pressure of AB and then the partial pressure of A. And again, we don't include B because of it being a solid. All right, next is on this graph, where would be these concentrations or pressures if this was either graph? And I'm just going to use red to say that any time, probably before this time frame right here, it looks like it's reached what's called equilibrium. So any concentration, like here or here, maybe that at time 1, or you could do this one and this concentration here at time 2. All of these would be a Q, and I talked about that being part of the Unit 5 kinetics section. And then anything over here would be a K value, and that's because if I say this is time 3, then I go to time 4. This isn't difficult. Look, it stayed the same, which is the definition of equilibrium, is that the concentrations remain unchanged. All right, or one of the definitions. So why don't I keep going to then what would this look like in a data table? But that would be what the reaction quotient is, and you calculate it the same way as a K. The only difference is we are not at equilibrium, so it's not the equilibrium constant, okay? But it's calculated pretty much the same way. So let's take a look at this data table, and I'm going to use the same reaction I have above with A plus B giving me AB. So if I wanted to, again, write the Q and the K, I'll do the same thing. Just going to put them right here. So again, my Q, but it'll be a QC, is going to be the concentration, my AB, over my A. And if I do calculate a K, C, it's the same thing. It's just what concentrations are going in there, and do we think those concentrations are at equilibrium? So how would you look at this data table and figure that out? It's actually not that complicated. So first, just kind of look for when do the concentrations stop changing? So if you kind of zoom in and say, okay, well, right here, from here to here, the concentrations are no longer changing, so we've reached equilibrium. Now, equilibrium was actually what's called established somewhere before that. So somewhere between like 21 to 39 seconds, or minutes. This one's in minutes, I think. Hang on, let me look and see. But I'm pretty sure this is in minutes, this data table here. Yep, so somewhere between 21 to 39 minutes, we had equilibrium was established. But we are now at equilibrium. So I'm just going to put those values over here kind of quickly here. So actually, I'll keep it in orange. So we're going to put that at that 0.015 and then 0.020. We are at equilibrium. And so the equilibrium constant ends up being 0.75 if you do all the math. So 3/4 basically. So then all the other concentrations that were before this are all what are called Qs, meaning that we're still not at equilibrium. The most obvious one is if we don't have any product, of course, we are not at equilibrium. So then what would be a Q value at one of these time frames? I'm just going to pick one. And I just picked one that I thought would give us some easy numbers. So we're going to use the 0.010 and the 0.025. I'll highlight where I'm at here. So I'm using this at 10 minutes. And what we'll get is that the QC here will equal, versus the K, will equal 0.40. And so what you'll say later on, you'll do this, if not even now, that Q is less than K. So we need more products. Now another way to say that, more products to reach equilibrium, equilibrium, such a big word, right? We might say that this is what's called shifts right. Later on, you might hear that. But that just means that the forward, we still have to make, you got to kind of go like that way. We got to make more products versus coming back when you have like the double arrows, coming back and making more reactants. The other thing is when Q equals, I'm just going to put that here, when Q equals K, then you are what's called at equilibrium. So I guess if you wanted to check like this value right here, it's still at equilibrium, you still get the same values. All right, on to our third thing on our one page of notes. I'm just going to kind of zoom back out again. Now we're going to move on to particle views. So how could we use particle views to decide the same thing? So the first thing I'm going to do is just go through and count. And to make the video a little bit faster, what I would do is, you actually should count all these. What I'm going to do is just to make this a little quicker, I'm just going to tell you what I've already pre-counted for my pictures that I've made here. So at the beginning here, we have 6 diatomic hydrogen and 4 diatomic iodine and no HI, the hydrogen monoiodide product, okay? Then at the next time frame, I'm going to count, and what I counted at that time frame was a 4-2-4, meaning 4, actually I'm just going to slide this one over because I'm going to do a little calculation with this one. 4 for this one, and then we have, 4, 2, 4, 2, 4. And then again, at the next time frame, I'm going to slide this one over to the left a little bit too because I'm going to do a quick little calculation. We end up having 3, 1, and 6, and then this stayed 3, 1, and 6. So using kind of, again, orange, we have reached equilibrium between here and here. We actually reached, equilibrium somewhere between the 16 to 29 seconds. This one's in seconds. And then we've maintained equilibrium as we've gone to the other ones. So what we're going to do is say this is a K value and this is a K value. And then all of these are going to be Qs. And the first one's the easiest one. Q is less than K because we don't even have any products. So we don't need to calculate the Q there. We know we need to make products. What I'm going to do also is put off the side here that this would be a QP that we're going to calculate. We're going to use partial pressures. So the pressure of HI, and then that would be squared. Because of the mole ratio right here, right there, okay? And then next would be the pressure of the hydrogen, and then times the pressure of the diatomic iodine. Okay, and then once we reach equilibrium, we would call it a KP, but it would be the same things. It would be pressure, I'm just gonna have to zoom in here to write this kind of small, pressure of HI squared. I'm just gonna actually get rid of this, get it out of our way here, there. And then pressure of the let's do hydrogen first, H2, and then the pressure of the I2, just to keep those the same. So when we do calculate that, that will be a K value because we will be at equilibrium, but you end up sort of like doing the same, math. Okay, so let's just quick do this. So how can we use our pictures to create kind of some partial pressures? So I'm just gonna go I would call it a little bit rogue here. There are 10 particles, so that means like 4 out of 10 is my partial pressure for my hydrogen. And then 2 out of 10 is my partial pressure for my iodine. And then 4 out of 10, again, is my partial pressure for my HI. So I'm going to use these kind of partial pressures based off of the picture to go find what the Q value is. So over here, what I'm going to do is just put those values in, okay? And I'll sort of zoom in. So I'm going to use red since we know it's a Q. And we know we're not at equilibrium until, close to 30 seconds, somewhere between there. So I'm just going to put these values in here in the right spot. So we have 4 over 10 here, and then we have 2 over 10 here. And then we have 4 over 10 again in the numerator. But we got to be careful, we got to square that. Now, what happens when we're done here, I'm just going to put it right here, is the Q is going to equal 2. So if the Q value, when I use these values, I'm going to put them off to the side here. So Q is equal to 2 right here. And what that means, again, is Q is less than K. So again, we have to shift right and create more products. So then what is the K value? How do we know that it's going to be less than it? Let's just put the numbers in, okay? So I'm just going to, again, count again and see if I can get like little, I call them like partial pressures from the particle view. So 3 out of 10, 1 out of 10, and 6 out of 10. And again, that's going to be our pressure of our hydrogen, our pressure of our iodine, and then our pressure of our HI. Almost done here. So then what is this actual value? Okay, so keep in mind these numbers went in for the Q. These numbers right here are going to go in for my K. So I'm just going to go over here and put these in here. So my K value, and I'll just switch to orange here. We're going to have 6 over 10, and again squared, and then 3 over 10, and then 1 over 10. And if you calculate this, it'll equal 12. So if this is the K value, well then definitely, if you calculated it, it's the same between here and here, right? I'll count the particles again if you need me to. However, we can see that 2, if you actually calculate Q was 2, so it's going to put over here, so Q was 2 and K was 12, well then we can see why at time, this goes together, these two. At time, at 15 seconds, our Q is definitely less than our K, and we had to make more products. All right, so that was a lot of colors and a lot of calculating, but you can see how Q and K are related and what really Q is. It's just we don't know if we're at equilibrium, and then if we do know we're at equilibrium, then we can assume that those concentrations are going to remain unchanged, whether that's in a graph where they're going to stay a straight line, whether that's on a data table where they remain unchanged, or in a particle view where you count your particles and they no longer are changing in amount.